Okay, good afternoon, everyone. Dr. Jensen here. So we're going to do a few practice problems here dealing with unit conversions. Okay, so I have marked a few of these problems. So these are mostly what I would consider to be easy or medium problems. All right, so we're going to start off with a few easy problems, and then we'll work up into the more moderate problems, and then we'll move into a more difficult or the harder problems in a subsequent video. All right. So when we're doing some of the early unit analysis, usually a lot of these revolve around simply converting from one metric unit to another. Okay, so this usually requires that we have the metric system memorized. All right, so let's look at a few of these here. Okay. All right, so if we have 515 kilometers, the question is how many decimeters is that? So we want to go from kilometers to decimeters. All right, so okay, as I was saying, if we have 515 kilometers or kilometers, and we want to know how many decimeters is that. This usually requires that we have some general understanding of what units are available as far as the metric system. So things that might come in handy here. Now, we probably don't have memorized a direct conversion of kilometers to decimeters. So you might go kilometers to meters and then meters to decimeters. So we know that in 1 kilometer, there is 1,000 meters, right? And then we know in 1 meter, there are 10 decimeters. Okay, so these might be your units that you would have memorized. So the question then becomes, how do we put these together? All right, so as I often say, the best way to start these is to start with the simplest term. The simplest term being the single unit for the kilometer. This is 2 units tied together by an equation, right, an equal sign. So there's a relationship here. So these are 2 terms versus 1 term. So we want to start with our 515 kilometers. Okay, and so you'll see me set this up. So we have 515 kilometers. All right, now I'll use these kind of railroad track setup here, this dimensional analysis. It's a little overkill for this kind of thing, but as we get into other more difficult problems, this setup can help us to keep track of what units are going where. Okay, so starting off, my next unit then has to be a kilometer. I want to set it opposite so that way it kind of tells you your step forward. So the first one has to be a kilometer. So the only thing that has the kilometer in it is this one. The top and bottom are the same as this equal sign. So 1 kilometer is 1,000 meters. Okay, so the top and bottom set up a relationship of equality. Okay, equals, right? So by putting it this way, by putting the 2 units opposite one another and putting these 2 units, I now have a kilometer divided by a kilometer, so that unit would essentially get canceled out. So if you stop right here, this would tell you how many meters are there. Okay, how many meters are there in 515 kilometers? Right? But we don't want meters, we want decimeters. So our next step is then in 1 meter. Again, setting the terms opposite helps you to know which one to go where, equals 10 decimeters. Okay, again, the top and bottom function as our equal sign. Okay, now the way this would work then is you would multiply all the numbers on the top and divide by all the numbers on the bottom. Okay, which is not difficult in this particular problem. Again, this is easy. So you get 5.15 times 10 to the 6th decimeters. Okay, that's 515 times 1,000 times 10, and then convert it to scientific notation. Okay. Next one, we have 3.345 kilojoules, and we want that in millijoules. Okay, so same setup as before here. Again, I only have one bit of information, so there is nothing else here as far as information to start with. Okay, so how do we get from kilojoules to millijoules? Now, there's probably not, again, a direct thing that you probably memorize to get you from kilo to milli. So we would want to go kilojoules. In 1 kilojoule, there is 1,000 joules, right? And then 1 joule, there is 1,000 millijoules. Oop. Joule, not a liter. Okay. So setting what's opposite here is going to be this first relationship, is kilojoules. So 1 kilojoule is 1,000 joules. Okay, again, my relationship demonstrates an equality between the two. And then in 1 joule, there is 1,000 millijoules. By setting these terms opposite one another, they cancel each other out. Okay, dividing a kilojoule by a kilojoule, the kilojoules go away. Dividing a joule by a joule, the units go away. The unit I was looking for was a millijoule. That's the only unit that's left here. Same thing holds. We're going to multiply all the numbers on the top, divide by all the numbers on the bottom, and then that will give us our unit in millijoules. So since I haven't changed anything else here, I still have 3.345, right? That number hasn't changed. And then it's times 10 to the 6th millijoules. Okay. All right, let's look at another problem here. Now, again, I would still consider these to be relatively easy, on the easy side. So these are now incorporating some of our use of density. Okay, so we know that density, is mass divided by volume. Okay, so ethylene glycol has a density of 1.1 grams per centimeter cubed. How much does 114 milliliters weigh? Okay, so we're given the volume and the density, and we want to solve for mass. Okay, so if you look at it from an equation standpoint, right, mass equals density times volume, right? That's what it should look like. Okay, so if we're doing this and we want to know where we're starting, again, the simplest term of the terms given in this case is my 417 milliliters. It is a simpler term. It is a single unit of milliliter versus grams and centimeter cubed. Okay. Now another way to look at this too would be 1.11 grams per milliliter. Okay, knowing that these two terms are identical. Centimeters cubed is a milliliter. 1 centimeter cubed is 1 milliliter. Okay, or 1 cubic centimeter is 1 milliliter, right? So this is the centimeter cubed. Okay, so these are the same thing, so they're used interchangeably. Okay, so we have 417 milliliters. Okay, now the density term here, because it's two terms, it actually looks like this. Okay, it is actually 1.11 grams for every 1 milliliter. Right, that's really what that's saying. Okay, so if we separate out, so I find that people don't, if they write these together, they often will include them both together in the bottom versus separating them as terms to where it's actually saying 1.1 grams per 1 milliliter. Okay, so now the 1 milliliter is the bottom relationship. 1.11 grams is the top relationship. Okay, so what do we have here? We have volume times the density, which is exactly what we would have expected over here. Volume times density equals the mass. So the units, therefore, the milliliters go away, leaving me with my mass. Okay, and so here we should get 462.87 grams. Okay, I'm not paying attention to sig figs here. Okay, so obviously that significant figures are a portion of this early part of the chapter. I'm just not paying attention to that particular thing at this particular moment because we would only have 3 sig figs. So technically, if we were doing this, this has 3 sig figs, or maybe has 3 sig figs, and that one has maybe 3 sig figs. So then our answer might have 3 sig figs, but it was a little ambiguous in this first one, so it's hard to tell. So I'm going to leave it like this. Okay. The reverse of this might be, and this is a little bit harder. This is still considered, I'm still ranking this one as easy here, right? But it's a little harder, but it's virtually identical. Okay, here we have mass, which is we're starting from a little bit higher mass. So again, we understand that density is mass divided by volume. Okay, here we have the mass and we have the density. So the volume then, right, would come over here and it would be a mass divided by density. Okay, so that should be the arrangement we see when we do the dimensional analysis. Okay, so we're starting from the simplest term, 4.1 kilograms. Okay, now we can't jump right into the ethylene glycol. The same density still applies. It's still 1.11 grams per milliliter. Okay, it's the same solution, just has 2 parts to it. Okay, so we can't jump right into using our density because our units or in kilograms don't cancel with a gram. So in 1 kilogram, there is 1,000 grams. Now we're in a unit that we can use. Okay, again, because the term is separated as this, the 1.11 grams is where I'm dividing. But what happens to the milliliter? Okay, if you divide by a fraction, it's like multiplying by the reciprocal. So the volume, so the milliliters appear on the top. So this means my kilograms are divided by kilograms, they go away. The mass divided by the mass goes away, leaving me only the volume term. Okay, and so if you multiply all the numbers on the top, divide by all the numbers on the bottom, parentheses are your friend if you're using a graphing calculator, you get 3.693 times 10 to the third milliliters. Okay, that is a 3 there. Okay, now if we were paying attention to sig figs, okay, this one has 2 significant figures, so then our answer would probably have 2 significant figures, and so it would probably really be 3.7 times 10 to the third milliliters would probably be the more accurate answer if we were doing this more precisely. Okay, so let's take a look now. All right, let's take a look now at a more moderate problem. Okay, here we're using a slightly different dimensional unit. Okay, here we now have cubed values. So the cube values, they're not strictly speaking different than the linear values. Here I'm converting meters cubed to kilometers cubed. Okay, so this still works. So we know that there's 1,000 meters in 1 kilometer. Okay, but this is a linear unit. This is 1 dimension. Okay, so if we take this and we turn it into 3 dimensions, right? Length, width, and height, okay? That same unit is just copied those 3 times. So we're essentially cubing the linear unit, okay? So you only have to memorize. So that's a great thing about the metric system. Once you memorize the units, you can easily convert this to a cubic unit, okay? So the same thing will apply here. Okay, so let's look at where do we start? Okay, so we're still starting from 115 meters cubed. All right. We'd still have in 1 meter, or I'm sorry, so 1,000 meters in 1 kilometer. Okay, so this is the linear unit. So a meter doesn't cancel with a meter cubed. So the whole conversion factor, you have to cube. Okay, you have to cube the whole conversion factor. Okay, so this means 1 cubed, kilometers cubed, 1,000 cubed, meters cubed. Okay, so when you put this in your calculator, it becomes 1,000 cubed. Oftentimes, this is easy mistakes that we find on a test question is where people just did the 115 divided by 1,000, where they may have written it out like this, but then they forgot to actually do the cubing. Okay, so you would cube this on the bottom, right? And then we would end up with 1.15 times 10 to the negative 7 kilometers cubed. Okay. And here it's multiplying everything on the top, dividing by everything on the bottom, but don't forget to do the cube of the 1,000. Okay. Last one here, same kind of thing. Here we're starting from a density term in grams per centimeter cubed, and we want to convert to pounds per cubic inch. Okay, so this is where, at least generally in my class, I would give you US unit conversions. So something that I would give you is tell you that in 1 inch, there's 2.54 centimeters. But again, this is also one that is good to have, that you would probably want to have memorized, okay? And also 1 pound is 453.59 grams, okay? And there's different versions of this. Again, people can give pounds to kilograms and things like that. So again, it doesn't, you would need to have some English or American to metric conversions, okay? Here, I'm just starting with the value that I'm given. Okay, again, the centimeters cubed, so this is 7.86 grams for every 1 centimeter cubed. Now, it doesn't matter which one you start with. Okay, you could start with the top or the bottom, right? But in this case, I'll just start with the centimeters. So we know there's 2.54 centimeters in 1 inch. Again, this is the linear conversion. So in order to turn the linear conversion into a volume conversion, we have to cube the whole thing. Okay, so what you might do then is write that cube value at the top here. Okay, that'd be 2.54 cubed. Okay, so that becomes the real number. So this gives me my centimeters cubed. and then there are 453.59 grams in 1 pound. So we multiply all of our numbers on the top, divide by all of our numbers on the bottom, and we get 2.84 times 10 to the negative 1 pounds per inch cubed. Okay. We'll come back with some other ones here shortly. I'll follow this up and we'll do some harder versions of some of these. Again, these are easy to moderate in difficulty, but definitely doable. And usually very simplistic ones that you would see for any type of chemistry test on unit conversion. All right, and so that is it for this video. And so I will catch you guys in the next one.